Yeah. Thanks for that. Welcome, everybody. Nice speaking. We are very happy to have Anand Sarwate from Rutgers today. A special training. Anand is has interest in information theory, privacy, security, optimization, machine learning, signal processing. So some of which we will hear about. To talk to him. Anand is a distinguished lecturer of the
He is also.
and he's also on the board of governors. Keep that in mind.
No, no, it's a sucker for doing anything.
And I don't know if you see that. Anand is a very nice singing voice. This radio supports such things.
Okay, thank you. Thank you all for coming. What I want to talk about today is some work that I've been doing, motivated by some collaborations that I've had with people in the more applied domain, looking at tensor factorizations or tensor decompositions and dealing with multidimensional data. So this is, of course, joint work. I can't do anything myself. So my colleague, Wahid Bajra, is at Rutgers as well. We worked with two students of earlier process work, Zahra and Mohsen. Batul just graduated. We'll primarily be talking about work that she did, and some of the experimental work was done by an undergraduate. That was a scientist who was visiting for the sun. Okay, so just to start out with, let's think about the word tensor. Like when I first encountered the word tensor, I encountered it in an abstract algebra class. So it was like not what I'm going to talk about today, but it has an earlier origin in physics. So the first use of the word tensor that we can find is from Hamilton. And actually, he used the word tensor to mean the norm of a quaternion. So his tensor is actually a scalar. So it's sort of confusing place to start. And then, moving on 50 years later, it starts moving into physics, mostly in German. And then Richie Corbastro developed a sort of more formal theory of tensors, and then he wrote a book with his student. The book was actually the thing that made it more popular. People could actually understand it. So I think the student worked better than the guys who taken those students. Then from then on, Einstein, or maybe most famous use is that Einstein and Grossman used tensor calculus to formulate general relativity. So these are two folks here. It turns out that I don't want to insult anybody. Physicists sometimes play fast and loose with some math. So then what we should do then Einstein had a bit of an exchange to kind of clean up some of the mistakes that Einstein made. And then in English, the first use of the word tensor is from a translation of a book by Milo, the Space-Time Matter book, which if you haven't seen before or looked at, it's actually quite nice. Read at least in English. I don't know if it's true. Okay, so what is a tensor? And so for purposes of this talk, a tensor is just going to be a multidimensional array. So one-dimensional array is a vector. A two-dimensional array is a matrix, right? And a three-dimensional array is a box. That doesn't have to have the same dimension on every side, right? And so I'm just going to think of it as a collection of numbers arranged in a rectangular shape. There are, of course, other ways of thinking about these things. This particular object can be interpreted in many different ways. It could be interpreted as a single point in the tensor product of vector spaces. It could be interpreted as a multilinear operator, where I look at each of these k coordinates and then I evaluate the function. I could also think about representations of the general linear group and Lie groups and stuff like that, which I don't really know much about, apart from some undergraduate memories of learning about them. But we're going to just think about, I'm a simple person, so we're just going to think about boxes. Right, and the reason that I think this is still an interesting way of thinking about things is that we have a lot of these multidimensional signals in practice. So in neuroimaging, which is the application which I'm most familiar with, you can think of a brain scan as a 3D picture of the brain. So it's a 3D image. In geosensing, you have things like hyperspectral imaging, where instead of red, green, and blue, you measure multiple points on the spectrum. So you have a whole series of sequence of values evaluating the Fourier transform at points in space. Of course, then in communications, where I grew up, you have things like massive MIMO. In these kind of settings, you get these things. You can also think of a joint distribution on several discrete variables as a tensor. You can also think about, say, vectorizing that. And or you can think about a time varying graph where you have the adjacency matrix of a graph, and over time it changes, and then that's like a 0-1 matrix, or maybe it's weighted. So we'll think of that as a tensor. The calculation bits of it, I think the first big application where you see a lot of these things are in chemometrics, but in psychometrics, but sort of evolved since then. So what do we want to do with this kind of data? Basically anything you want to do with like 1D or 2D data. So we'd like to do things like signal recovery. So a brain image, right? Or a brain rather, and I have a way of imaging the brain, right? And so then the brain, I want to understand this process. How do I go from the physical world to this image? You could have unsupervised learning problems like representation learning. I would like to be able to compress, for example, a brain. So then you have supervised learning, where maybe I have this set of brains here. You have healthy and diseased brains. You'd like to find a way of separating them into two classes. That's supervised learning prediction. And so you might ask, well, what is this? So you understand who's going to. I'm leaving on the 21st, so I will miss this naturally. Between and so the diseased brains obviously are moving for England, and of course the healthy brains are no improvement in this image. So yeah, so if you want to do compression, you also it's kind of kind of follows on from learning with representations. So particularly when I started working on this problem, we were looking at a problem called dictionary learning. So in dictionary learning, I give you a bunch of tensor data, and I would like to learn learn a dictionary such that I can represent each of these data points with a sparse number of dictionary points. So look to find a parsimonious representation. So they're all of these xij's, these x coefficients, only s of them are not zero for each of my data points. Great. And so one application for this kind of compression would be to, if you have a drone or a plane doing hyperspectral imaging, you might want to compress that data before sending them, say, the world wirelessly. In supervised learning, in classification or regression, you have a bunch of labeled pairs of points. You have x, which is a tensor, and y, which is a scalar label. You want to find a tensor, a regression tensor, such that the inner product between x and b is, a good model for your response. So the model is a linear. So this is a known inner product. And so, for example, and this is things that my collaborators are interested in, is being able to predict or estimate either a health condition or some other property from. One thing that people are really interested in is estimating brain age, because it's sort of on the road to understanding this stuff. Well, how the brain ages. I will that's back from the top. So thanks for that. So right, so there's a question like, okay, I could just vectorize this thing. It's just a vector. So that is exactly good. Didn't plant him. Gave me the honestly by this question honestly. So a baseline approach is to just reshape the whole thing, right? So you could take this hyperspectral image, right, and you could turn it into a one big array, right? It would be a 1 by say 550,000 array. So this image is about 100 by 50 by 110. You could reshape it into, you could take slices and kind of arrange them into a 2D thing. So you think about that. And then once you've done that, we have lots of methods out there for dealing with vectors, lots of methods for dealing with matrices. So we just put it into the machine, turn the crank, and then you would you'd have to fit a model to this kind of data. So you're doing linear regression, you'd have to fit 550,000 parameters. And if you were, say, using a vision transformer or something like that, the huge version is 632 million parameters. So you want to fit this number of parameters, and the question is how many. In particular, if you're looking at brain scans, it's not very large. So the problem of doing, say, vectorizing tensor like this is it ignores, in fact, any structural information you have about the fact that this purple cube and this red cube are next to each other. I mean, you can preserve some of it, but you're sort of losing track of that information, or kind of ignoring it. And the problems that you get are going to have very high dimension. And so, for example, if you look at a data set of MRI images on ADHD, it has images of children's brains. This is a data set that you can find and experiments with. So the fMRI data is 121 by 141 by 141 tensor. After vectorizing, you get a 2 million, dimensional vector. And the sample size you have in this data set is about 950. So from 959 images to estimate 2 million parameters is absolutely a big ask. Right? So this is, of course, not a problem just with tensors. And so what do we do when we have this issue with too many parameters and not enough data points is we make some assumptions, some restrictions on what the structure of the thing that we're trying to estimate. So if I have a linear model like this, in vectors, for vector data, you would sort of assume that it's sparse. You assume most of the entries are 0. For matrices, you might model it as low rank. So I'd say, like, we have this big matrix, but in fact factorizes into the product of these. Now I have fewer parameters to estimate. But for tensors, you actually have many different choices for how to do this. For vectors, sparsity is pretty natural. I would argue, and for matrices, low rank is also pretty natural as a kind of structural thing. So in this talk, I'm going to talk about some of these restrictions and then talk about regression. Actually, for 3, I'm probably going to not have time for this. So I'm going to talk about some application areas. Before I get going, any questions? I know that I'm happy to take questions at any time. So thank you for breaking the ice. That isn't necessary. I'm saying low rank is a natural thing. Not that it's human, but like there are sort of natural candidates, and there are the decompositions. You have many different natural candidates. So I don't want to like an opinion statement, not a factual statement. Okay. So unfortunately, you go and you say, "Oh, I want to learn about tensors," and then you immediately get confronted with kind of confusing at first notation, terminology. So I'm going to subject you to that now, hopefully in one slide. So we have this cube of data. You have 3 dimensions. So say there might be dimensions m1 by m2 by m3. And we can think of this cube is made up of vectors. I can think of n1 dimensional vectors and 2 dimensional vectors and 3 dimensional vectors. I can split it up like French fries here. And so we call these 3 dimensions here modes. There are 3 modes at the order of the tensor is 3, and the fibers are these spectrums. Right, and so for this hyperspectral image, mode 1 and mode 2 mode 1 is the spectrum, so that's the vertical axis here, and then modes 2 and 3 are latitude longitude. So if you're interested in a good introduction to tensors, there's a paper by Kolda and Bader, a really nice survey, and another survey by this. It's more popular, like has a more updated version. The Kolda and Bader, though, is a nice thing to start. All right, so we can take a tensor and we can multiply it by a matrix. So I could take, say, an R1, R2, R3 tensor G, and I could multiply it along mode 1 by a matrix B1 that will expand out. So I can expand out or compress that dimension. So we get, and that's equivalent to basically taking this matrix and multiplying vectors to the figure, right? So multiplying this matrix times each one of these. So one example of doing this in this hyperspectral image is if I want to apply a filter to this spectrum, I can think of it as applying the same filter to every fiber using this normalized. You can of course chain these together, so I could take a tensor here and write it as a factorization of the right? That's some small thing expanded out in 3 dimensions. V1 expands it out in 1 dimension. They're multiplying the other modes. And so this is how you can get a tensor X to have a smaller representation because the number of parameters in this factorization is smaller than the number. So the problematic thing about tensors is the notion of tensor rank is not there are a couple of notions of tensor rank. So a rank 1 matrix, the rank 1 tensor is just the outer product of 3 vectors. So 3 in this case 3. So it's a 2D is a rank 1 matrix. So we can think about rank R matrix as a sum of rank 1 matrices. We can think of a rank R tensor as a sum of R of these inner products. So something that looks like this. And this is called the CP. So if I can write my tensor as a sum of these rank 1 terms, then that is decomposing it in the CP representation. I can sort of more compactly represent this as taking some box in the middle, which has got only things on the diagonal elements, and then multiplying it by these 3 matrices that stack up. Stack up the different factors over here and put the alphas. So this is a CP decomposition. If my tensor gets a CP decomposition, it can be written like this, where this core tensor G, called the core tensor, is diagonal. And so the number of parameters, instead of being the product of all of the dimensions, is now like the sum of them. Let's look at it. Great. Of course, now if you write it, if you write things like in this, you're like, well, why is all this space in the box? I should be able to put more things, fill up the box. So you fill up the box and you get something called a tensor. But now you have 3 ranks. You have R1, R2, and R3. So it's a rank vector that you have for your model. So you have a core tensor T, which is this R1 by R2 by R3 thing. And then we can expand the dimensions using these tensor products, and this Tucker decomposition then has all the elements in this parameters, all the elements in this T, which is the product of the R's, and then all the elements of these matrices, which is the product of them. So these are the standard decompositions that sort of see first off. Now there's also people say, well, this is not flexible enough. I would like to do more. So what you can do is pick, so in some ways, yes, and in some ways, no. So there's like uniqueness issues and stuff like that, which make it. It's not like, oh, I have the SVD and this is the SVD. Only one SVD. Right. Yeah. So there's and so here it's a bit more complicated and frustrating. So. The block tensor decomposition, you could just say, well, why don't I just take a mixture of these guys? So instead of just having one of these, I'll just make many of them, and so you can sum them. So then I would just multiply S times this number of parameters, and that would be the parameterization of my model. I could even be even fancier and like make all the G's different sizes and all the B's different sizes, and just go to town and give myself all the modeling freedom in the world. But then I run back into this problem of how do I fit the parameter? So the CP rank is the smallest number of terms in the CP decomposition. So you can always write a CP decomposition of a tensor. You can see this because I can get each coordinate individually by taking the outer product of element frequencies. So I can always write it out as like a gigantic number of terms, but there's a minimal number of terms. This decomposition is often unique, but not always unique. So that's one annoying thing. But also, it's computing the rank as well. So it's NP hard for the rationals and random fields and so on. For the theoretical computer scientists, are probably well aware of this. The Tucker rank is a vector. If I give you the ranks, you can try. If I know that the thing has a certain rank vector, I can use something called a higher order SVD or some other algorithms to use factorization. And it's not. Right, so this kind of answers some of your question here. It's messy. When you dealing with things in like this kind of format looks nice as it's a simple equation, but computationally, at least, might be a little bit. You might want to work with it. You might want to interpret what's happening differently. And so instead of just vectorizing the problem from the get-go, you could ask, what if I vectorized under the constraint of the structure? What would I get? Right. So I could flatten the tensor. I can rearrange it. I can vectorize it in a couple of different ways. So I can arrange it into take slices and pile them. So if I know that my tensor, for example, has a Tucker factorization, if I then vectorize my original, so here's the Tucker factorization. If I vectorize B, Tucker, right? If I vectorize it, then I can write it as a vectorized version of G multiplied by a matrix with a very special structure. This matrix is the Kronecker product of all of the factor matrices. So for those who remember the Kronecker product of two matrices is make copies of one matrix inside the other one multiplied by the coefficients. So now you do this k times and you get this gigantic matrix. It will be gigantic because G is probably somewhat large. And the dimensions of this thing are going to be, the product of the R's by the product of the N's, and the original tensor is quite large, like that 550,000. This matrix will be 550,000 by something, but it has a nice structure. So maybe we can work with it. That's the hope. So what we propose doing is we sort of saw that the existing factorizations were either too simple or way too complicated to actually work with the kind of data that we need. So we decided to look at a restriction where we do look at a sum of terms, but we make all these G's the same. These core tensors the same. We call this a low separation rank composition for a reason that I will get to in slide or two. So the key thing is that we're using the same core tensor, which means that all these B's have the same dimension, so we don't have to think about that level of flexibility. And we can sort of assume that the B's have orthonormal columns and sort of shove everything into. So now we have like a more structured problem to think about. And now we can think about optimizing, fitting a model by optimizing over these different things. That's the approach. Right, so this is a we call this low separation rank, and why do we call it that? Is that if we write out, if we have a matrix which we know is the Kronecker product of a bunch of matrices, then the minimum number of terms needed to kind of in the sum to decompose a matrix is called the separation. This was used by Silikaridis and Piro to look at covariance matrices. So our so great question. I got this question. Well, I got this question. I gave a version of this talk over the summer, and then I'll say the same thing because unfortunately I don't really know that much about quantum. Writing out that separable state though, it looks like it is. And it looks like the CP decomposition corresponds to some superposition type of thing. So I don't know what this would end up meaning for a quantum system, but it could be. I'd be interested in knowing. learning. Great. So, our this LSR model assumes basically that we have the same core tensor here. So this big matrix that I was talking about, which is the Kronecker product of all these factor matrices. Now I'm taking the sum of those. That's the that is a mixture of Kronecker product structure matrices. That's the thing here. Now this is the highly structured, but in a unpleasant to think about dimensional. Right, and so what you get is this kind of trade-off, sort of bias variance sort of trade-off, where you have like a small number of parameters in the CP decomposition, or some larger number of parameters in the Tucker decomposition, and basically we're looking at kind of a mixture of these Tuckers, but in a very constrained way. And then up here you have this block tensor decomposition, which is like the one plus. So the nice thing here is that we can add more terms if we have more data, or if we want a larger number. So we get to control how many parameters we have, as opposed to sort of having to stick with one, stick with these limited number of parameters, but also we don't have to accept sort of arbitrary stuff. Okay, so then the question is this useful? And experimentally, the answer is yes, but like let's talk about the theory of it first. So I want to talk about regression problems. So I'm going to give a break for questions. Yes. Yes. Yeah. Because of this, if you look at this structure here, they don't stack up. It's not. It's like it's the sum of products, not but you can't factor it out into this product of sums. Yeah. So I too was asking this question. So that I'm assuming that yeah. Okay. So we're going to look at generalized linear models, because we want to try to do the most general thing possible. So basically, we want to estimate a parameter if in an exponential family model, where the responses are for an exponential family, and the parameter eta of the exponential family is the dot product. So this generalizes linear regression and logistic regression. So if you look at logistic regression, it's the Y's model is a Bernoulli parameter, and that this distribution only depends on the inequality. So you can also do Poisson regression, interregression, and other types of regression with more exotic functions. So of course, as I said before, what we found is for some of the applications we were interested in, we thought having a little bit more flexibility in some things that would be beneficial. Yeah. Yep. Well, just element-wise, dot product, dot star, some dots like dot star. Or star and some. And so, I guess, correspondingly, we're going to be looking at all the norms that we look at here. So we're looking at LSR models for LSR structured GLMs, but other works have taken like different combinations of this. So have CP and logistic regression, you have LMs, you have Tucker and linear regression, you have logistic regression. So we're sort of following along this line of work, which and it's a lot of these papers are really interesting. Highlight perhaps this paper by John Hall. So if we want to understand this problem, what we need to understand is what is the structure of our constraint set. Right, so we need to understand what is the set of LSR structured matrices. So it's the number is the set of tensors, it's the set of tensors, set of distributed factor V factors. So it's a set of tensors that's going to be represented in this factorization. Correct, but basically the set of things we want is under the orthogonality constraint. So we have to optimize over this space in order to select a good model given our data. So you can then say, well, great, I'll do maximum likelihood. You then kind of somebody who's, you have to write out what the maximum likelihood estimate is, and here's the maximum likelihood estimate. It's not very pretty, but you can try to minimize it. You have to minimize this. If I do the matrixization, you have to minimize this LSR structured matrix with the sum of these product or products and this G, and you want to minimize this, maximize the likelihood or minimize the likelihood. So from an algorithmic perspective, what we're going to end up doing is alternating minimization, or we just cycle through and take it. But we want to understand kind of the space of what is the space we're optimizing. But first, so we need to understand if we want to put bounds, what are like packing and covering numbers for this space. So if we want to find lower bounds on, we want to find number of, we want to find lower bounds on sample complexity. We can use the Fano method, and if we do that, we spend a lot of time constructing very carefully a set of packing set. We can get something which scales like what we want. Like it's the number of the scale. The exponent is the number of parameters on the model. And to do this, we have to actually, this goes back, so now that I can be an information theorist for a brief second, we actually are using some ideas from like superposition coding and using the local Forshaw codes to get a packing at the hypercube, putting them together to prove some bounds. There's a little bit of trickiness in handling for generalized linear models over linear regression. So that's why it's a little bit trickier, because we need some extra assumptions to get the divergence between two models. Great. So yes, good point. I probably should have had something. So let's wait for that. Great. So I would like to know two things. I would like to know if I would get a unique solution here by minimizing this, and how many samples do I need to get a solution that's within a certain epsilon of the true. And I'd like to know if you don't give me enough samples, how am I going to, if I don't give you enough samples, I want to be able to show you that you will fail. Any estimator will fail. Right. So to show that any estimator will fail, I have to essentially exhibit to you models which two sets of the B's and G's, for which the observed data that you get, the XYs that you get, are going to look very similar, pale divergence. So from a hypothesis testing sense, they're kind of indistinguishable. But they're actually very far apart in Frobenius. That is, so they actually the numbers look very different, but the data that they generate. And I'd like to generate a large number of those. The question is, how many can I generate such that I get this this property where for every model there's another model which is actually far away from it in terms of the numbers that are in the B's and the G's, but in fact which generate very similar. And so the scaling is going to be exponential the number of parameters, hopefully. Oh, right. So this is the in the exponential family, it's the eta transpose T is the special spaces of the if you can construct such a packing, then you can get a bound like this, which says that the Frobenius norm squared error, the expected squared error of estimating a true tensor B star that any estimator B hat, this error is going to be at least so big, and so big is going to be the samples for parameters. So we can, we can see the number of samples and the sample. So this result actually generalizes the prior results for the set, because the Tucker and CB models are simpler special cases of we have, and so you get kind of a table that looks like this. We get these kind of bounds here, and this generalizes some previous lower bounds. So this is good. This is a lower bound, though it's very pessimistic. So the question is, how good is maximum likelihood? And so for that, we need to actually find a covering number for that same site. And the covering number also has the same scaling. And this is actually much easier in some sense, because we're kind of just pasting together covering numbers for the factors. You can sort of paste together and then do a calculation to make sure that we don't lose extra error. So this will translate into a sample complexity upper bound, which matches the lower bound. You get kind of a favorite characterization of this problem. The only issue is, of course, that that the optimization, this requires you to exactly minimize, maximize all the likelihood, and which is it's the non-convex space to deal with. So we do alternating minimization, which is basically what all the works do. Those algorithms with some few exceptions. And so if we are doing this, alternating minimization, where we minimize each of the factor matrices, then minimize over the core tensor, and go back, scoop around. We have to, for these ones, we have to, for these green boxes where we minimize over the factors, we have to do a projected gradient descent, because we need to make sure that the things are orthogonal. If these are orthogonal, this is actually turned out to have a little bit of trickiness, which I can talk about offline about whether or not QR factorization that we use is compressive, or it's yeah, it reduces distance. So that was a little unclear. And then we can just use regular gradients. So with this approximate optimization, we can then try to throw this. We have kind of a nice theory story, so we can try to throw it at some problems and see what. So you could look at applications of this modeling. And so the first one we looked at was in regression on. So we looked at this fMRI data set on autism called Abide, and also something looking at geography, looking at blood vessels. So other algorithms that are out there, you can do some kind of, basically the main difference. I mean, there's the differences in the estimator, in the estimation algorithms, but it's basically in the modeling. So the question we're interested in here is like whether the extra flexibility in the model is helpful. So they all have terrible acronym names that are not pronounceable. So okay, so if you look at a tiny data set, in a 2D case actually, with only 80 samples, so the question is that there's a big grain of salt we have to take with all these results. It's around 80 samples. So how meaningful are these results? We can by expanding the model a little bit, we can get a better fit to the data. The unstructured models, in fact, just are not worth reporting because they're so just end up fitting. You basically interpolate particularly good. And what this told us is that adding just one more Tucker component in our mixture is actually even that much is actually effective. You see this also in other applications. If we look at the vessel in this thing, it's got a bit of a larger sample size in 3 dimensions, and we can get pretty small core tensor ranks like 3. So and we can again choose only 2 factors and go. So we're not trying to say that we don't have a good way. So I'll answer the question before somebody asks it. We do not have a good way of choosing. So that's always the problem. So all these issues such as overfitting and interpretability are still there. You can actually do this. The reason that I am interested in this, problem is because I'm working with some folks on a system, and the algorithms guy, on a system that's supposed to allow neuroimaging researchers to collaborate, do joint analyses of neuroimaging data. So this is a system called Stack. And so there you have different research groups which have collected data on some condition, say Alzheimer's or some other brain health condition. They can't share the data. And so you'd like to be able to do a kind of a message passing algorithm, a federated learning algorithm, in order to, say, learn a predictor for Alzheimer's out of this data. We actually, I'm not making this problem up. This is a real type of system that we're using. And we have had a collaboration with like multiple countries here in Japan, Germany, US. I think China is the best way. So one issue, I'm working on privacy. So one issue is negotiating all the privacy issues with this kind of setting, but it shows a kind of proof of concept that actually leveraging this larger sample size is really helpful. And so we wanted to know, can we do this can we sort of plug our algorithm in with this sort of natural way of making it federated by kind of emulating centralized algorithm. And it turns out that it requires you to really keep very tight coupling between the things. You can't like do a bunch of local computation and then update, which is kind of the ideal where you can minimize the amount of communication. You really have to communicate every gradient step, basically. Otherwise, stuff diverges. So that's what we see experiment. So this is what the Younger does. But if you do have the ability to pass messages, you are willing to do that much communication, this method works, but it also suggests maybe other algorithms that have certain better communication methods. Not communication complexity in the CS theory sense, but number of bits being communicated. One thing, just as an aside, in this system here, number of rounds of communication is a real issue because you have to maintain persistent connections across to these multiple sites, many of which have put their data behind a firewall. So actually, from a practical standpoint, it's desirable to have 2 rounds if possible. In the interest of again, I said when I started at the beginning of the talk, I talked about dictionary learning. So in dictionary learning, just to remind you, you have your measurements Y, and you're battling them as like some linear combination of columns of D. That's in the vector case. And you're saying that Y is only uses a small number of columns. Each Y uses a small number. So I need to learn this dictionary such that each sentence only uses a few words. That's the metaphor being used here. So this is the model. We call these dictionaries atoms, and these XI selecting columns. So the question is, what if my Y's are not a vector? So the traditional approach to doing this would be to vectorize the data. That this gigantic dictionary that's so we can actually go from, we initially started just looking at the Tucker model where you have this Kronecker structure thing to a mixture of Kronecker structure matrices with this LSR structure. And so if you apply the LSR decomposition to the dictionary, you have a much smaller number of parameters to estimate the dictionary. And there's a paper in transactional signal processing you can look at. It really works a lot better for denoising applications. To do something like this, then the kind of name would take a regular, just a unstructured. So we also have theoretical results for this dictionary learning problem. You have these same kind of sample complexity bounds. You have a local identifiability, meaning if you start me out near the true solution, I will get there within that sequence. We don't have like a global identifiability. So we have a mini-max lower bound. So we have a lower bound that says you need this many samples. Those almost match. And actually there, it's kind of interesting from the construction. It's like there's some wastefulness that we can figure out how to do that. And we have a couple different algorithms, some of which can be done, can work in an online learning way, some of which not. And as I said, they have some good results. So all this is to say that, all this is me like advertising, trying to say that this kind of slightly more complex model is useful. I'm trying to convince you. This being able to do this instead of just one term like this is helpful, and then giving yourself all the freedom in the world to like arbitrarily shape things is too much freedom. So this hopefully will let you adapt the parameterization to your data available. And I think that despite the fact that everybody wants to do big data was so let's go back. I'll be able to say big data. Actually, a lot of problems are small data. Medical imaging is small data. Large dimension, but small data. So we still need these kind of. And if you, even with just adding one more term, you can still estimate the parameters relatively effectively. But I think there's lots of interesting work to be done in not just with this model, but in general, this kind of problem. So on the theory side, for example, we don't really have good results on just denoising. If I give you a noisy tensor, if I tell you this tensor has low range, and then I ask you to do I have an algorithm that will, get me some, will denoise, will actually, get me remove some of the noise. We don't have like the clean results like you would like to have for, say, SVD. You take the SVD, you know that you're getting rid of the noise dimensions. We don't have that kind of result. There's a lot of sort of topological topologies that happen when you deal with these kind of tensors. Like you got a limit of rank R tensors where the limit point is an R1 tensor, R plus 1 tensor. So like sets are not closed that you want to be closed. So you get on the one hand, like from a math perspective, you're like that's bad, and then if you think about it from a practical perspective, you say that's never going to happen. You can somehow work around that. We are doing alternating minimization. Maybe there are convex relaxations that we use here. There are some other types of factorizations. One thing I think is really interesting would be looking at random tensor theories, random matrix theory minimization. So, in that sense. And then, of course, there are applied application problems. Looking at, I put real in quotations because, I can only make so many claims to be working with real data. But there's lots of other data domains where I think we haven't really looked at it very much, such as hyperspectral imaging or metrics. One thing which you can do and seems to work, at least empirically, a couple of anecdata from some experiments they're running, is you could try to compress, use this factorization to compress with segmented boost pressure, especially for convolutional layers. And you can also use this idea in generative modeling to kind of provide a different kind of, already methods kind of put some structure on the embedding space in say, autoencoders. You can use this to provide different structure on autoencoders and get sense. At least anecdata. Yeah. So lots of interesting questions and lots of interesting theory questions. Thank you for your attention. And thanks for hope your backs are good too. So thank you. Yeah, like I mean, the old school way of doing this would be canonical correlation analysis. And I mean, I think that the small sample size here comes from like the small number of individuals that we actually have for that brain scheme. In studies of mental health disorders like schizophrenia, you're lucky if you can get a sample size of like 25 cases. And that's again local, because you need to have 25 people with schizophrenia diagnosis to follow the protocol. And so what you're doing is reusing the data that you collected in that study, but hopefully leverage with the data from other sources. There's lots of practical problems or issues with this. They used different scanners, which have a different number of Teslas in their magnets, with different knob set. So there's all sorts of issues. Like the theory is all like everything is IID, happy theory land, proof bounds. But in practice, you get the sort of these kind of problems. But like what you're trying to do is get 50, 50, 50, 50, and then get like a sample size of 500. With a sample size of 500, you might be able to say something with a little bit more. And so, in order to get what you're talking about, you would need to not only have taken an MRI, but also an EEG, and also this and that, and have collected all, which people have for some some of these studies, but then you require each of the sites to have collected all of these things. That makes it other than that setting, just for that. For other applications, you're totally right. Where you can collect data from these, or you already have collected data. This one, so we can say, hey, this is different, but in practice, it just destroys. So I am